welcome to this final class on Naval Architecture 1. And what we want to do today, mainly first want to go through the final set of notes, which is very short, on the introduction to transverse stability. So I've sent these notes to you, where in these notes we introduce the concept of transverse stability. As we said earlier, in chapter 4, we introduced that there are stability can be seen in two aspects. One from the transverse stability point of view, and the second one is from longitudinal point of view. So from transverse stability point of view, we are looking at the port and starboard movement, or the effect of stability in the port and starboard direction. So we are looking at the ship in this way. So yeah, and in fact in chapter 4 we were looking at the first part of the transverse stability, basically the effect of GM, yeah, the metacentric height on the transverse stability. So in this chapter we are looking at the continuation of that. So not only that we can determine the GM, but we can also determine the effect of moment applied on the ship and its effect on the angle of heel or angle of list. Okay, so in this 5.1, if you can read, you can understand what we are talking about here. Basically, the ship is normally meant to be upright. In normal condition, we want the ship to be upright. But in certain condition, when it is improperly loaded, then there'll be out of balance moments, which may cause the ship to list. So the ship will list heel. Basically, is movement of the ship in the it's like rotation of the ship, yeah, rotation of the ship about its center of gravity to the port or starboard of the ship. A list is more permanent. So when we say the ship is listing at a certain angle, then it is normally caused by a bit more permanent movement of center of gravity, and because of that, the moment is there. Okay, so then we call the ship to list. So when we go to port, for example, when we see the ship is is listed to one side, it means that it is there for quite some time, and most of the time it is because of the movement of the center of gravity is no longer exactly in the center line. But heel is a bit more temporary. It's a quasi-static. So sometimes you just push the ship to heel at a certain angle, go to 5 degrees, maybe to 10 degrees, and then you release it and so on. So the ship is healing in the like quasi-static, yeah, angles, but it will stay to a certain position when it is listing. Okay, right. So when we move weight on board, particularly, so the first part that we're looking at here would be if we move weight on board. So if we move the weight just in the transverse direction, okay, like this one, for example, originally say this weight is somewhere in the middle here, and you have this small weight, yeah, this small W is here. Then you move it to the side like this. So before it is its movement there, this will be the relationship between K, B, G, and M. Yeah, this is K, keel, B, center of buoyancy, G, center of gravity, and M, which is the metacentric height. In this case, it is in transverse direction. But as we said in the previous lecture, we said that the M, when we look at this, we know this is MT, of course. It's not ML. Yeah. So this is a normal ship. But once you, and of course, there are two forces on this ship at this time, which is a force of weight pulling down here, and the force of buoyancy going up there. And we can put this as W, or we can use this L delta, the same thing, which is the buoyancy will be the displacement delta, or the weight, which is also the displacement W, which is also equal to delta. So you can use either of the, I should have used delta here so that it's not confused with this WL. This is water line. This W is water line. So I'll need to change this. This should be WL, water lines. This should be delta, like I've tried to do here. So I change this one to weight, delta, yeah? So in fact, the buoyancy here is also delta. So because in equilibrium, weight is equal to buoyancy, or the displacement is equal to the weight. Right. So if we move this weight here, we know from our chapter 4 that the center of gravity will move parallel to the movement of the weight. So if you move the weight here, G will move this way to G dash or G1. All right. So when it goes here, there is no change in terms of the GM. The GM will still remain constant. Yeah, because it only shift in this direction. But there'll be a G is here. So the weight is pushing up here, and the buoyancy is still pushing up here initially, yeah. So because of that, there'll be a clockwise moment pushing the ship, rotating the ship, so that it is becoming like this. So that the center, so that the center buoyancy will go underneath the G1, which is the shifted center of gravity, the new center of gravity, so that the force of delta here, or the weight here, or the buoyancy, sorry, the buoyancy here, delta, will be the same as the weight pushing down. So they are now in equilibrium. So this is the in equilibrium, right? So at this point, it goes here until to the point that the center buoyancy is directly under the center of gravity, and it goes through up through the M. So M is basically the point, as we see, will not change. So this M will not for small angle, M will be constant, so that the center of buoyancy will go center of gravity and will go through M. Okay. So in this case, you see that the volume displacement is shifted to the right, and that's why the center buoyancy is to the right here. So in this triangle, G, M, and G1 here, sometimes we put G dash, sometimes we put G1, which is the shifted center of gravity. So this is the triangle. And from the triangle, we can get the angle of heel that we can get from there. So because triangle G1M here, tangent of the angle is G1 divided by GM. Yeah, the angle of this angle is phi. Phi is phi, the Greek F. This is phi. So tangent of the phi is G1 over GM. And from our previous class in chapter 4, we know that the shift in center of gravity, okay, G1 is W times D divided by W, or divided by delta, which is the original weight. So the tangent of phi is W times D divided by the original weight, or the displacement of the ship, times GM. So this formula is very, very, very important for us to remember. You're going to need this throughout your life as a naval architect. Tangent phi is the listing moment. Listing moment means the moment that is listing at the moment. Like this, basically, the listing moment is the weight move from the center line, it move here. So this weight times D, the distance move here, divided by the displacement of the ship, which is the delta here, and times GM. So W times D divided by GM. So whatever that, in this case, the listing moment is W times D, because the weight move from here to here, the distance D. Okay, but in other condition, the listing moment may come from something else. Okay, maybe it's not because of weight movement. Maybe somebody is pulling, for example. The ship is upright like this, and then or just a boat, and somebody come and put their hands here, from in the water and put the hand here, right? So by putting the hand here, the we are putting a moment. So that moment, it depends how much we pull the side of the ship, the moment, right, about the center of gravity. So that moment that is being put there is the listing moment. And again, the angle of heel, or the angle of list, sorry, listing, is listing moment divided by the displacement times by GM. So it can be seen that GM plays a big role in determining the angle of list, because GM is in the bottom. So if you have a big GM, tangent phi will be small, and small tangent phi will lead to small phi. So the bigger the value of GM, the less the angle of least, and vice versa. So that means if you have small GM, for example, 0.0 something GM, then even with a small listing moment, you have a big phi. That means that angle of least will be very much affected by this GM for a certain fixed displacement. Okay, total weight of the ship is not changed. But if you list, so if you pull a big weight, you move a big weight, okay, or a larger distance, then you have a big listing moment, and because of that, you have a bigger angle of list. Yeah. So the final position of center of gravity, and hence GM, is found by taking moments about the keel and about the center line as discussed in chapter 4. So we know already. So GM, in chapter 4, we know how to find GM. So in this case, we are looking at how GM is going to affect angle of field. So let's see for this example. A ship 6,000 tons displacement is floating upright. It has km 7.3 and kg 6.7, and it's floating upright. It's floating upright here twice. Yeah. Okay, so you can delete this one. Result. So, uh, place because the 7.3 minus 6.7. So this information enable us to calculate GM, which is here. So this one is equal to 0.6 meters. Okay, it's not good like that. All right, 0.6 meter. Okay. No, it's okay. I'll correct that later. So GM is km minus kg. It's given here, 0.6 meter. So tangent phi is listing moment 60 by 12 divided by 6,000 times multiplied by 0.6 GM. So tangent phi is 0.2, and we get the list to be 11 degrees 18.5 minutes. Yeah, so this one should be minutes. If you use your scientific calculator, you should get that. Okay, so this is it's correct. Okay, I think 80.5. Or we can remove that one different. It's 18 minutes. Right. So that's basically how you calculate that. and you can do the exercise. The exercise has exactly the same question. In the first question is the same one, but with a different km. Yeah? So you go to the exercise, which is right at the bottom. It says carry out similar calculation example 5.1 with kg 7. So if you have say kg to be 7 here, right? If kg is 7, then gm is 7.3 minus 7. So gm is not 0.6. It is 0.3. So if you have 0.3 down here, you take your calculator. Can you just try to take your calculator? You have a calculator around you. I'll get my calculator here. Sorry. So scientific. Have you done any calculation there? Can share calculator. Because we need scientific calculator to calculate that. I couldn't find my scientific calculator on the. Okay. Right. So it will be 60 by 12. 6,000 by times 0.3. Okay. 6,000 times 0.3 equal to 1,800. 1,800. Okay. So 60 by 12 is 720. So multiplied by 720 divided by 1,800 is equal to 0.4. Okay, so the tangent phi is 0.4. If the kg here is 6.7, sorry, 7.0. So here becomes 0.4. So in that case, then your the tangent shift tangent 0.4. So we get the angle to be 21.8 degrees. Okay, which means that, but just changing of kg by 0.3 meters cause this angle to be, instead of 11 become 21.22 degrees, almost twice. Okay, so which is we show the influence of GM, yeah. So but just by changing GM 0.3, you have made the ship more, the listing more, yeah, which 22 degrees is already quite dangerous, yeah, because normally we say that maximum that we can allow the ship to list is about 15 degrees. Beyond 15 degrees, it is already on the danger ground. Yeah. Okay. So that is basically if you move weight on board. So you can see the exercise. The exercise is all about this formula. You see, like this one, a shape almost exactly the same as example 5.1. Okay, but example number 3 here is a bit different because it says that we want to get the angle, okay, the angle to be 2.5 degrees. And the question is, find the distance through which a 15 tons weight already on board must be shifted. Okay, so this is a bit strange, but it's still the same formula. What you do is, you take this formula, okay, you still take that formula, but now you, sorry, the original formula is here, right? But you now know that this is tangent 2.5 degrees. You know W, which is the weight to be moved. You don't know D, You know the total displacement and you know GM for that exercise number 3. Yeah, exercise number 3. So it is still the same formula, okay, but just you rotate it, you just to find D. And for the number 4 is still also the same. During an inclining experiment, a 3,000 tons displacement ship. So we know this displacement of the ship, we know the weight, we know the distance, okay, and we know the angle that we got, 3 degrees to starboard. Right. So the question is, if km is 6 meters, find the kg. What does it mean? From this information and the formula, okay, which is this formula actually, yeah, same one here. From this information, this formula, we can get GM because we know angle, we know the listing moment, which is 10 times 12, and we know the original the displacement W or delta to be 3,000. So we know we can find GM, right? So if we know GM, we know KM, then we can find KG. All right. So this is actually very, very, very important for you to remember, because this is actually the way what we call as conducting of inclining experiment. Later you in network architecture 2, you're going to learn about inclining experiment, and you're going to use this method and this formula to actually calculate the kg of the ship. Not calculate the kg of the ship, to measure or to determine the kg of the ship. And this is actually a practical thing that is happening in all shipyards. That means that all ships that is going to be registered must undergo inclining experiment. And when they do the inclining experiment, the purpose is, one of the purpose is to determine the kg of the ship. So to determine the kg of the ship, they move weight on board. And once they move the weight on board, they use this formula, okay, the formula that we learned today. Okay, something that later if you work in a shipyard and the shipyard wants to do inclining experiment, what you learn today is the one that you're going to apply in that particular case, yeah, of inclining experiment. Okay, so that is basically that part. The second part of this notes, okay, the 5.2 is finding list after loading and unloading. As can be seen in chapter 4, I should have put this section. I was trying to cross-reference to section the section in chapter 4, yeah, regarding loading and unloading of weight aboard, which we have learned. Okay, by loading and unloading the ship, if you load all the loads in the center line, then basically the only effect is the changing of center of gravity. See, so you take one load, for example, from outside. Say the ship is upright here. So you take one load, you load in the center line. You load here. Okay, first if you load here, if you load the ship, the load from outside at the center of gravity, there is only a change of total weight, total displacement, total buoyancy, but there is no change in center of gravity and there is no change of list. Okay, but if you load the weight anywhere along this center line, okay, you look down here or you look up here, then there will be two effects. The effect is, number one, change of center of gravity. So the center of gravity will go up or down depending on where you load the vessel. So if you load here, for example, you look on top. Shall I get this pen? Get the pen. So if you load here, if you load here, then G will move up. So G will move up. Okay, and so maybe this is the new G now, G dash. So by loading something up here, G will move to G dash. So GM will be reduced. Weight, total displacement will be increased. Okay, so if you load here, if you load in the other direction, okay, so if you load in the other direction, right? So you load, instead of loading here, you load down here on the center line. That same weight you put here. Then G will move down because you load below G, then this is the new G. So this is the new G. Okay. So loading up or down will increase or decrease the center of gravity. Will it decrease like this? The GM now is reduced. This is the new GM. If you load up above there on the deck, for example, on the main deck, or if you load down here, then this is the new GM. Sorry, the new GM will be from here to here. Increase the GM. So if you say you want to increase GM, then you load downstairs, load down below G. If you want to reduce GM, then you load above G. Okay, so that's the first point. So now, if you load not at this point, for example, okay, you load here from outside, not something that's already on board. You load something there. Okay, so if you load something from outside here, the effect will be three effects. Effect number one, G will move to here and here. So it move, of course, it move actually just to G dash here. Okay, G dash. Okay, G dash. So it actually move like this. You move towards the point at which you add the weight. So this is the new G now. Okay. So by loading here, the height of G has increased. So the GM become reduced. So this is the new height. The vertical height of the center of gravity is measured from this line to M line. So y of you the new distance W. So it's W times D is the moment. And this is a clockwise moment. So this clockwise moment will be the listing moment that will be turning the vessel. So we go to right. So for after loading, there are three things that happen. Three things that we need to do. Yeah. First, we find the final kg. Okay, final kg we find by looking at how much it has gone up. The G dash, yeah, in the y direction, the vertical direction. And then find the net listing moment, port or starboard about the center line. And then use tangent phi formula to find angle of least. So this is, for example, this is you put already two load and one discharge, one unload. Yeah, a ship originally 5,000 tons, kg 7.6 meter is loaded as follows. So you load 100 tons at kg 6.1 and a location 7.6 meter to starboard of the center line. Load 200 tons at 0.6 meter, kg 6.1 meter to port of the center line. And discharge 70 tons of ballast, kg 1.2 meters, and height center gravity 4.6 meter to port the center line. So you have three items being loaded. If we were to draw, always we want to try to understand, then we need to draw it. So say this is the original G, okay, and then so now you add 100 ton kg 6.1, so maybe original G is 7.6, so this is 7.6, okay, so you add this one kg 6.1, so it'll be lower, so along this line, and the center of gravity, sorry, okay, along here, and 7.6 to starboard. So if this is port, this is starboard, so this is somewhere here. Just say that. Okay, so this is 7.6 meter, and this is 6.1 meter. Okay, and then you load 200 tons kg. I think I'll redo this here. Sorry, make it bigger, make it like this, and the center line there. Okay, so this will be G, be higher. This will be the original G, which is 7.6. This is 7.6, yeah. I'm not using a mouse, so it's a bit difficult. So this is 7.6, the original kg. 7.6. Okay, so the original G. Now you load this one. The height is only 6.1 kg. The point to the starboard is 7.6 meter. Also 7.6 meter. So you load somewhere here. Okay, the location is this one. Okay, so this point. So this is 100 ton here. Okay, and then you load 200 to port 6.1. So we somewhere here. Sorry, this one here. This is 200 ton. Okay, and discharge. Okay, this is loading, eh? So that means that the weight are all pushing down here. So this is the weight of 200 tons, and it's the weight of 100 ton. Should use a different color. So this is weight of the 100 ton, and this is the weight of the 200 ton. Okay, and then you discharge 70 ton. Kg 1.2, center gravity 4.6 to port. So there is somewhere here, maybe, it is discharged. So we put the arrow that way. When it is discharged, it's a weight as if that we've lifted out the weight. Okay, if you add, the weight is pushing down, pushing down. So this distance is 4.6. Yeah, so this is 4.6, and this height is 1.2. Right? So first, of course, the first step is find center gravity after loading and unloading, which you can do. Okay, you put the weight 5,000 tons. This is chapter 4. 5,000 tons, kg 7.6. Okay, and then 100 ton, kg 6.1, and then 200 tons, kg 0.6. Right, and then this one minus 70 tons, kg 1.2. So you add all the weight, you're going to get 38. This is not correct. No, this is not right. Okay, we need to check this. We need to check what's the final displacement should not be this one. This one might have been copy and paste from somewhere else. I need to correct this as well. So the weight here, 5,000 plus 100 plus 200, that is 5,300. Okay, minus 70. So the total weight is only 5,230. All right. So total weight. So this is not correct. So this one we need to remove this. This is not correct. Okay, so we find the final weight and the final moment, and you divide the final moment divided by the weight, you get the final center of gravity. So we will need to correct that and then resend it to you. And then find the moment. So this moment seems to be correct. Okay, the moment is correct because, right? So the moment is what we saw just now. Okay, so from this moment, yeah, so you see that 7.6, 7.6, okay, 100, which is this one, the distance is 7.6 to starboard. So we put the moment on the starboard column. And then my 200 times 6.1 on the port. And then minus 70 times 4.6 to port as well, which is this one. So this one is minus 70. And it is minus 70 to port. So the net is you take this one, you minus this one, and you add this one. Because 760, it should be port minus starboard minus port. So 760 minus 1220 minus 322. So you get 138 to port. That means the port moment wins. Okay. So because it wins, that means the ship is going to heel or to least to port. Right? Betul pula kat sini. Here, this one is correct. So since the net moment to starboard, the ship will least 5 degrees to starboard. Right? So tangent phi is listing moment divided by this. So the final listing moment is 138 to port. So divide by 5230. So 5230 is correct. It's total displacement. And this one, if you calculate the GM correctly, somehow this is something not right. Something not right. Can check. Then you should get the 0.661 GM and finally get the point. Okay, I'm going to correct this and resend it to the class later, the notes, yeah. So that is basically the for this particular class, yeah. Okay. Now we can so that's basically it for this particular class. We just need to use this formula, okay, to calculate the angle of the listing angle of the ship after movement of weight on board. That's the first 5.1. Okay, 5.1 is after moving weight on board. This one, okay, and this one is after loading and unloading. After loading and unloading. So when we load the ship, then so this actually maybe you can do your own exercise. Find the kg final here, and then you put your actual kg. I hope this is 0.61. Then you can still use this. Okay, so that is for this particular sets of notes, our final set of notes, right? And this one is to go through the online quiz. not many of you has done the online quiz. This is the online quiz is this one. Okay. So far only 7 responses out of 40. So I'm a bit worried about your colleagues who do not attend this class, do not attend the classes, and also not doing the the exercises. Yeah. So number one, all these are very simple because it's very similar to the class example, the notes example in notes, or in the exercises, and we have seen the exercises solution. But I'll just go through with the solution. A ship 2000 tons displacement has kg of 3.1 meter. Find the GM of the ship when 100 tons is loaded on deck with kg 5 meter and kmt after loading is 3.21. So always when we have a question like this, like just now in our example, we always have this table. So this table is called loading table. So, and in the loading table, we do not forget the original ship. There must be original ship. So original ship, weight, kg, and the moment about kill. What's this one? Okay, moment about kill, 6,200. So you add the cargo there, add that kg, and you should find the final kg. So very simple. Okay, and then if you go to the next one, a ship displacement 2,400 tons, kg 11.05, kg km 0.05, kg 10.8. Find gm when weight already on board is moved to deck. Deck. Okay, weight already on board. Yeah. So it's just a matter of movement of weight. So this weight is moved from 0 kg 0.5. So it is similar to just that sheet that we saw just now. It is like this. So you have a weight from down here. Okay, and move up. So that movement is actually, how far is it? It's 12 meter movement, right? 0.5 meter to 12.5 meter. So the movement up here is actually 12 meter. Okay, so just vertical movement, GG dash, is weight move times height divided by displacement. So it's 0.25 meter. And new, so you can get the new kg by adding the original kg 10.8 to 0.25, so 11.05. And that so happen that same as km. So gm is km minus kg, so it is 0. So we see that in the first question as well, the gm that we get in the first question is very small. Okay, 0.02, which is very small. So dangerous for ship. This one is even worse because it is 0. Okay, so maybe the question can ask you comment on the stability of the ship, right? So you need to know that for GM, okay, GM should be greater than or equals to 0.15 meter. Okay, always ensure, okay, GM greater or equal to 0.15 minimum. Cannot be less than that. If you are less than that, especially like this 0 and 0.02, these are all dangerous. Yeah. Okay, so that's number 2. And number 3 here, achieve displacement dispatch, following cargo is loaded. So you load, find final GM. So it is simple enough. You take the ship, you load. There's no unloading here. Okay, so just load and put the kg, find the total moment. Okay, find the total moment, and finally you get the kg, the final moment divided by final displacement. So it is this one. See the formula here? H56 divided by F56. So you get this 4.25. Okay. So since you know given KMP is 5.6, it's given here. If KMP after loading 5.6 meters, find GM. So you get that. Okay, and the final question, actually testing your ability to understand, not this one. Okay, the question is here. Okay, so the final, there was some correction or corruption of the video while we were recording the class. So for this question number 4, so I'm continuing question number 4 using PowerPoint presentation. So this is the solution to question 4 for the quiz in chapter 4. This is a question inside the Google quiz. Hydrostatic particulars of bunga pisang is given, and while in port, a mean draft of 6.25 was recorded. Then kg was 7.5 meters. So and then this thing loaded, the cargo 1, fuel 1, hot fuel oil, and unload cargo 2. So the question is calculate the population loading, the mean draft, kg, and GMT. Okay, so to do that, first we need to know the original ship. What is its displacement? Yeah, so to know that, we have the mean draft here given 6.25. So we go to the hydrostatic particulars. 6.25 is not here given directly, so you need to interpolate between 6 to 6.5. So we get in between here, what's its displacement? Once we get the draft 6.25, we know all the hydrostatic particulars. But in this case, we don't need the rest. We only need how much is the displacement here. So when we calculate that, displacement is 9075 tons. So we put the details inside this loading table again. The original ship 9075, kg is given 7.5, and then the load of cargo 1 fuel oil and cargo 2 unloaded also given. So we have all this data. Just calculate the moment again, sum up the moment, divide by the total weight, and we get the kg to be 7.15. Right. So now we know the total weight is 11,480. So if you go back to the hydrostatic particulars, at 11,480, the draft is already given at 7 meters. No need to interpolate. You're lucky. So, and we get all the hydrostatic particulars at 7 meters. In this case, we are interested in KB plus BMT, which is this one. 3.26 plus 4.46. So 3.26 for KB at draft of 7 meters and BMT 4.46. So GM is KMT, which is KB plus BMT minus KG that we got initially in the initial calculation, in the loading table calculation. So we get the final answer to be 0.57. So the question is, what's the draft? 7 meters. What's the kg? Kg is 7.15 or something that was given that we calculated just now. And this finally the GM is 0.57. So that's the answer.